Micromachined back markers on thin film of scaffold effective to measure repetitive contraction myotubes. The speaker's affiliation changed several times, started with mechanical engineering, research on tribology, then moved to School of Medicine, Archer Heart, electronics, biomeasurement, and created the first department of biomedical engineering in Japan, bachelor, master, doctor courses, cell and tissue engineering. Came back to mechanical engineering. During these affiliations, the speaker experienced a variety of collaboration with medicine, thoracic and cardiovascular surgery, orthopedics, plastic surgery, neurosurgery, anesthesiology. The movie shows repetitive contraction of myotubes cultured from myoblast of mouse synchronized with electric pulses, frequency, in vitro. My present affiliation, Kogaku University in Japan, has Micromachining Center and Cell Culture Center, which supports this study. The slide shows outlook of micromachine devices made in our laboratory. Microgroove trap, microslit between microcylinders, microslit between ridges, microridge with variations of intervals, and micromarkers on the rear side of thin film. How do you measure repetitive contraction of myotubes? Can we mark a local point on myotube itself? To design scaffold of polydimethylsiloxane, several factors need to be checked. Marker size smaller than cell diameter, short interval between markers to measure local movement, transparency for optical observation. If you choose to put marks on the scaffold should make movement synchronous to that of the myotube. The scaffold should have the same level of elasticity as the myotube. To design scaffold of polydimethylsiloxane, several factors should be checked. The elasticity of the scaffold that balances with the contractile force of the myotube. The affinity between the myotube and the scaffold must be sufficient to synchronize with each other. Hydrophilicity for cell adhesion. Surface topography affects cell alignment. The protrusion of the surface changes the elastic properties of the scaffold. Does the backside microridge affect the mechanical properties of the scaffold surface? Surface hardness may be related to the durotactic of cell migration. The myoblasts are cultured. They are differentiated into myotubes. Myotubes make cyclic contraction synchronous to cyclic electric pulses applied to the medium. The slide shows the concept to detect local deformation of film by tracings of micromarkers, which are made as micro-protrusions on the rear side of the scaffold thin film of PDMS. When the myotube makes contraction, the synchronous movement occurs. on the scaffold thin film. The slide shows arrangement of markers. Micro-protrusions of the hemisphere shape, diameter of 4 micrometers, are arranged on the rear side of the scaffold thin film of PDMS with interval of 30 micrometers. The thin film is sandwiched between cylindrical rim supporters of PDMS. The slide shows photolithography process to make photomask for arrangement of micro-protrusions, titanium coating, photoresist coating, laser drawing, developing, etching, and photoresist removal. After many trials, dimension has been selected for markers and thin film thickness. Dimension of manufactured photomask was measured by laser microscope, which shows the diameter of each marker as 4 micrometers, and the interval between markers as 30 micrometers. Photoresist coating is controlled by several factors: viscosity of photoresist, rotating speed of spin coater, baking temperature and time, and intensity of laser drawing. Dimension of the surface topography on the mold is measured by stylus profiler to confirm design parameters: thickness of film, interval between markers. Mechanical properties depends on the volume ratio of PDMS to curing agent. PDMS ring in a diameter of 15 mm was placed on the thin film of PDMS. After the film was baked with the ring, PDMS film with PDMS ring was carefully peeled off from the mold. Scanning electron microscopic SEM image of the backside of the film of the scaffold. Micromarkers are successfully made with the interval of 30 micrometers. C2C12 mouse myoblast cell line was cultured on the scaffold film. After 9 days of culture, myoblasts were proliferated and differentiated into myotubes. The slide shows the experimental system during electric stimulation: culture dish with electrodes, microscope, and electric stimulator. The slide shows the electrodes to dip into the medium in the culture dish to stimulate myotubes on the scaffold film by cyclic electric pulses. Myotube contracts on scaffold film with micropattern markers by electric pulses stimulation. The movie shows cyclic contraction of myotubes observed through transparent thin film of PDMS. Several parameters are measured on the film: distance between markers of several combinations, angles between X and the longitudinal direction of the myotube. The movie shows cyclic contraction of myotubes observed through transparent thin film of PDMS. Several parameters are measured on the film. Distance between markers of several combination, angles between X and the longitudinal direction of the myotube. The distance between markers X are traced at the microscopic movie image during cyclic contraction of myotubes. The amplitude A was measured by the difference between the maximum value and the minimum value at the cyclic variation of X. The tracings are analyzed with several parameters: angle of theta between X and the longitudinal direction of the myotube, and the distance d from the contracting myotube. The detected amplitude A of the cyclic movement decreases with the distance d from the contracting myotube. Using the approximated line relation between A and X, A is normalized to the amplitude ratio R in the next figure. The amplitude A is normalized to amplitude ratio R using the approximated line relation between A and X. The amplitude ratio R is constant regardless of the angle theta. Conclusion 1. Repetitive contraction of myotubes has been measured by local movement of micromarkers on thin film of scaffold under electric stimulation in vitro. 2. Scaffold is made of thin polydimethylsiloxane film thickness of 6 micrometers, of which backside has arrangement of micro-protrusions 4 micrometers diameter, 2 micrometers height, interval 30 micrometers, made by photolithography technique. 3. C2C12 mouse myoblast was cultured to be differentiated into myotubes on scaffold for 12 days. 4. Contraction of myotubes by electric pulses is observed through transparent scaffold at microscope. 5. Experimental results show that amplitude of cyclic variation of distance between micromarkers depends on distance and on alignment. 6. Designed scaffold can analyze local contractile movement of layer of myotubes in vitro. The slide shows references. Thank you for your attention.